Welcome to the course on Python for data analytics, machine learning and generative AI. In this session, we will focus on statistics, which forms the backbone of data science and machine learning. This session covers finding the center of the data, measuring the spread, central limit theorem, Z-score versus t-distributions, analyzing categorical data, and errors and statistical powers. By the end of this session, you should be comfortable applying statistical concepts using Python and interpreting results correctly. Statistics for data science involves understanding data behavior. It helps us summarize information, measure uncertainty, and draw conclusions from samples. In Python, statistics becomes a powerful tool when combined with libraries such as NumPy, Pandas, and Scipy. One of the first steps in data analysis is finding the center of the data. We learn how to find the center of the data. The center tells us what a typical value looks like. There are three main measures of central tendency: mean, median, and mode. The mean is the average, but it is sensitive to extreme values. The median is the middle value after sorting the data, and it is more stable when outliers are present. The mode is the most frequently occurring value. In the example shown, the value 100 is an outlier. Because of this, the mean becomes very large while the median still represents the data better. This shows why median is preferred when the data is skewed. Finding the center alone is not enough. We also need to know how the spread out of the data is. This is called variability. Range shows the difference between the maximum and minimum value. Variance measures how far values from the mean are on the average. Standard deviation is the square root of variance and brings the spread back to the original units. The graph shows two curves. One curve is narrow, meaning low spread. The other curve is wide, which means high spread. Understanding spread helps us judge consistency in data. Real-world data often involves randomness. Probability distribution help us model this randomness. The uniform distribution assumes all outcomes are equally likely. An example is rolling a fair die. The graph looks flat because no value is preferred. The binomial distribution deals with discrete outcomes. It models the number of successors in fixed trials like coin tosses. These distributions help us simulate real-world uncertainty using Python. The normal distribution is one of the most important distributions in statistics. It is defined by two values, the mean and the standard deviation. The curve is symmetric and bell-shaped. About 68% of the value lie within one standard deviation. 95% lie within two standard deviations. Almost all values lie within three standard deviations. This rule helps in deducting outlier and building confidence intervals. Many real-world variables approximately follow this pattern. The central limit theorem explains why the normal distribution is so powerful. Even if the original data is not normal, the distribution of sample means becomes normal when sample size is large. Here, the population data is messy and non-normal. But when we take many samples and calculate their means, the result becomes a smooth normal curve. This allows us to apply normal based test like t-test on real world data, providing the sample size is sufficient. A point estimate gives a single value such as sample mean. However, one value is often not reliable. A confidence interval gives a range of likely values for the population parameters. It is calculated using the estimate, critical value and standard error. The visual shows multiple confidence intervals from repeated samples. Most intervals capture the true population mean. This helps us understand uncertainty in estimation. When to use Z distribution and T distribution is very important. Z distribution is used when population variance is known, which is rare. The curve is perfectly normal. T distribution is used when population variance is unknown, which is common. It uses sample variance and has fatter tails. The fatter tails means more uncertainty. Because of this, the critical value of T distribution is larger, giving wider confidence intervals. Now, we start with the null hypothesis, which represents the status quo. We choose a significance level, usually 5%. The rejection regions are shown at both ends of the curve. The p-value tells us how extreme the observed result is. If the p-value is less than alpha, we reject the null hypothesis. If it is greater, we fail to reject it. This framework helps us make data-driven decisions instead of relying on guesswork. One sample t-test is used when we want to compare the mean of single sample to a known or assumed population mean. Let us look at the scenario given here. The question asks, is the average age of Minnesota voters differ from the national average age of 43? Here 43 is our benchmark or reference value representing the national mean. To answer this question, statistically, we first set up our hypothesis, which means assumptions. The null hypothesis, denoted as H0, states that the Minnesota mean age is equal to 43. Alternative hypothesis, denoted as HA, states that the Minnesota mean age is not equal to 43. This makes it a two-tailed test. Next, we apply the one sample t-test using Python. The function tt_test underscore one samp compares the sample mean with the population mean. The output shows a t statistics of minus 2.57 and a p-value of 0.013. Now, let us interpret this visually using the t distribution curve shown below. The red shaded areas on both sides represent rejection regions. The observed t-value falls into one of these regions. Since the p-value is less than 0.05, we reject the null hypothesis. This means there is statistical evidence to conclude that the average age of Minnesota voters is significantly different from the national average. Now we try to compare two groups, independent groups and paired or dependent groups using t-test. First, let us look at the two sample t-test, also called the independent t-test. This test is used when we are comparing the means of two unrelated groups, such as the voters from Minnesota voters versus the voters from Wisconsin of US. Here, each group consists of different individuals. The Python function t_test_int is used for this purpose. Setting equal underscore where is equal to false makes the test more robust when variances are unequal. Next, we move to the paired t-test, also known as dependent t-test. This t-test is used when the same subjects are measured twice, such as weight measured before and after a fitness program. The key idea here is that each before value is directly linked to an after value. Because individual variation is controlled, paired tests are usually more powerful. At the bottom, we see a sample table showing before, after and the change values. The paired t-test actually works on these differences, not the raw values. Now we shift from numerical data to categorical data and introduce the chi-square goodness of fit test. This test helps us answer a simple question. Do the observed category counts match what we expected? The formula shown calculate the chi-square statistics by summing the squared difference between observed and expected values, dividing by the expected value. On the left, we see observed counts for 3 categories and next to them the expected counts. These expected values usually come from theory, past data or a known distribution. Using Python, we apply the chi-square function by providing both observed and expected values. The output gives a p-value of 0.0011. Now, look at the bar chart on the right. The blue bar represent observed value and the strip bars represent expected values. The visible gaps between them explain why the test result is significant. Since the p-value is less than 0.05, we reject the null hypothesis. This means the observed distribution does not fit the expected distribution. The chi-square goodness of fit test is widely used in surveys, market research and social sciences. Chi-square test of independence is used to examine whether two categorical variables are related. The research question here is political party affiliation independent of race? To answer this, we first create a contingency table. Each cell in the table shows the number of individuals belonging to a particular combination of race and political party. Next, we use Python's chi2_contingency function. This function calculates 4 values: the chi-square statistics, the p-value, degrees of freedom and expected counts. The decision rule is simple. If the p-value is less than 0.05, we conclude that the variables are dependent, which means there is a relationship. If the p-value is greater than 0.05, the variables are considered independent. This test is extremely useful in sociology, political science, healthcare studies and business analytics, where relationships between categorical variables are frequently studied. Let us start with type 1 error, which is shown in red, and this occurs when we reject a true null hypothesis. In simple terms, it is a false positive. The probability of making this error is called alpha, usually set at 0.05. Next is type 2 error, shown in blue. This happens when we fail to reject a false null hypothesis. In other words, we miss a real effect. This is known as false negative and it probably is called beta. Now, statistical power is defined as 1 minus beta. Power represents the probability of correctly deducting a real effect when it truly exists. Higher powers means a better chance of finding meaningful results. Power increases with larger sample sizes, stronger effects, and lower variability. Understanding these errors helps researchers design better studies and interpret results responsibly. Summarizing the session as a decision guide for choosing the correct statistical test. The first question is to ask what type of data do I have. If the data is continuous or numeric, we move towards t-test. If the data is categorical or count based, we move towards chi-square test. For numeric data, ask whether you are comparing means. If you have one group compared to a benchmark, use a one sample t-test. If you have two independent groups, use a two sample t-test. If the sample group is measured over time, use a paired t-test. For categorical data, ask about your goal. If you are comparing observed counts to expected counts, use chi-square goodness of fit. If you are checking for a relationship between variables, use chi-square test of independence. The key message here is that Python provides the tools, but you must provide the correct context and reasoning. Statistical inference is not just calculation, it is informed decision making. So let's open Jupyter Notebook write some Python code together and bring the concept of statistics to life. Thank you.